Okay, in this example we're going to look at this truncated circular cone and find the X and Y and Z positions of the centroid, again using composite shapes. If we look at this object, one observation we can see is that it has symmetry. Because of symmetry in the YZ plane with this shape, we know that our y will be 0, our y bar will be 0. And because of symmetry in the xz plane, our x bar will be 0. So now we just have to determine what our z bar is. So we'll be looking for z bar. When determining z bar and using composite shapes, we have to find a shape that looks like this. And right now, if we look in the back of the book, we see these shapes. And the one that comes closest to the shape that we're interested in is this cone itself. The problem with this cone, of course, is that's not what we have. We've got some truncated cone, right? We've got this part which has been removed, this upper portion. But we can probably use this with some composite shapes and add two shapes or subtract some shape off to get our shape that we're looking for. So if we look like maybe at an overall cone itself, and then subtract off a smaller cone, we can get our truncated cone. The trick in all of this, again, is to maintain our x, y, and z coordinates from the original. So let's take a look at how we could do that. So again, here's our original problem. If we go forward, we see that we can create this new, we can create the truncated cone using a large volume of V1 and then subtract off V2 at this location, which is 4 inches up. Okay, so that's the way we're going to do this. And if we look at this in our equation, and again the denominator has the volume, we need to find the volume for this. And in our equation in the back of the book, we see that the volume is equal to 1/3 pi r squared times the height. The question is, we know the r squared, we know what r is for the large cone, and we know r for the small cone, but we don't know the height of the other cone. Let's go back here. We don't know, or how do we find this height? It's shown in here, but how do we come up with that? And we can do that by similar triangles. Let me show you that real quickly. Okay, let me show you how we find that height, that 8 inches, by using similar triangles. So we know this from similar triangles. We are given that this is 3. Our top cone is given as 2. Right? We know this dimension is given here as 4. And that is from here to here. And then we have a dimension of h for the overall height. So we can set up a ratio using similar triangles. This dimension in here is h minus 4. So if we do that, we have h minus 4 over its radius of 2 is equal to the 4, or I'm sorry, for the large triangle we have h divided by 3. We can then solve for h, right? We will get 3h minus 12 minus 2h equals 2h, sorry, and then we can solve for h, and h will equal 12. So that gives us the overall height of 12, and that gives us this to be 8 inches. So that is how you solve for that height. Okay, knowing that, we can now use our table again and solve for our two cones. So the first one is the large cone. We have the very large cone. We have is, again, the volume is 1/3 pi r squared. R is 3 times the height is 12. This equals 113. For the bottom one, we do 1/3 pi. The radius is 2 squared, and the height of this one we said was 8. This is for the small one, and we'll be subtracting that. This volume ends up as 33.5. This is volume, so this is inches cubed. Okay, so if we add this up, these volumes, we have 113 minus 33.5. We end up at 79.5 inches cubed. The next step is to find our z tilde. So this, if we look at it, is the distance to the centroid. So this is 4 over h. So if we look at our large cone, which we had before, we are looking for the 1/4 h of the large cone to this xy plane. So this distance down to here. That is our z tilde. And that is defined again by h over 4. H in our case here for the large one was 12 divided by 4, or 3 inches. And for the smaller cone, we had 8 over 12. 8 over 4. This is our h. If we go back, that is here. This distance is 8 over 4 plus this distance here of 4 inches, because we have to get back to this xy plane. So if we look at that, this is equal to 2. 2 plus 4 is 6. Okay, so if we take the z tilde times the volume for the large one, we will get 3 times 113, or 339 inches to the 4th. And then for the small cone, we end up with a negative 201 inches to the 4th. If we add those up, we're taking the 339 minus 201, we get 138 inches to the 4th. Okay, the last step then for our z bar is to look at, again, the sum of the z tilde volume divided by the total volume, or in our case 138 inches to the 4th divided by 79.5 inches cubed equals 1.74 inches. And that will be the location of our z bar. Now it's good usually to kind of check to see if that seems to make sense. So it was 1.74, so it's somewhere in this location here, which kind of makes sense that it would be down in the bottom more because we have more volume towards the bottom.